Hello, welcome to another OMG video for A-level chemistry. Today we're looking at electrochemical cells. We're going to do the whole of electrochemical cells in one video. Yeah. Let's get started then. We're first going to look at standard electrode potential. Now this is your definition here. So it's the potential difference between the standard hydrogen electrode and any other system in which the concentration of all active ions in solution is 1 mole per decimeter cubed and all gases are at 1 atmosphere pressure and 298 Kelvin. Now the first thing you noticed them say was the standard hydrogen electrode. This is my standard hydrogen electrode. I've got in there a platinum electrode. This is inert, okay? Inert is brilliant because it doesn't react. I've got hydrogen gas going in and I've got a solution containing hydrogen ions, so most probably an acidic solution here. Now this is what we call a half cell because it is half of our full electrochemical cell. On the other side I've got an example of a half cell. I've got a copper half cell. First thing you'll notice is this time I haven't got a test tube. I've got a metal electrode. That's because I'm looking at the electrode potential of the metal copper, and I've got a solution containing copper 2+ ions. A couple more components then. I've got a salt bridge. This completes the circuit. It allows ions to flow. I've got wires which carry electrons, and I've got a high resistance voltmeter. Okay, this is going to measure the potential difference of the cell, and the reason why it's high resistance is because I want to prevent any backflow of electrons, especially when our potentials are quite close together. Now just to really tell you what we are measuring, okay, with the standard hydrogen electrode, this is quite wordy. We're looking at the tendency compared to hydrogen of an element to either lose electrons, so become oxidized, or gain electrons, so become reduced. Just go into a bit of detail then about what this means, okay? The standard hydrogen potential is used to measure the ability of a half cell to gain electrons or lose electrons. First of all, half cells with more negative electrode potentials prefer to undergo oxidation. So I'm thinking of elements like iron, zinc. They've got negative electrode potentials. Think of your metals here, okay? Elements which love losing their electrons, also ones like sodium, potassium, group 1, magnesium, group 2. We know they react by losing electrons. Now, when they become oxidized, we act as reducing agents. So something with a really negative electrode potential is going to be a reducing agent. Half cells with more positive electrode potentials prefer to undergo reduction and therefore act as oxidizing agents. So I'm thinking of elements that want electrons here. Think of fluorine, chlorine, bromine, iodine, oxygen. They all want to gain electrons in reactions. And finally, my electrons will move from the more positive electrode potential to the more negative electrode potential. Now, there are 3 different types of half cells, and there's a method of representing these half cells. First of all, we're always going to note the reduced form, and then we're going to note the oxidized form. This is common to all 3 types of half cell, and this is really useful because it allows us as scientists to have a quick shorthand way of noting cell diagrams rather than having to draw them every time. So my first one is a metal and metal ion solution. Example of this could be copper solid and copper 2+ ions, okay? So first thing I'm going to do here is my reduced form, the one with more electrons, is copper solid. My oxidized form is copper 2+, and that is aqueous, okay? We've dissolved that in a solution. Now the big thing you'll notice is that one is a solid, one is aqueous. I'm in different phases, so I'm going to draw a line in the middle to separate those phase boundaries. Type 2 is a non-metal gas with a non-metal solution and an inert electrode, okay? Example here is the hydrogen electrode, okay? Now when we haven't got a metal to carry electrons for us, we have to use a platinum electrode. And we use platinum because it's inert. In other words, it will not react. Okay. Now, in a hydrogen electrode, we know we have hydrogen gas and we've got hydrogen ions. So the first thing I'm going to do, my reduced form, there, my one with the most electrons is hydrogen gas, so I've got H2. And my oxidized form is H+, and that's aqueous, so I'm going to need to split up those phase boundaries. My last one is a solution containing 2 metal ions and an inert electrode. So this time, let's have an example. I could be using Fe3+ and Fe2+ ions. Again, I haven't got that metal electrode to carry those electrons, so I'm going to be using an inert platinum electrode. I've now got my reduced form, which is Fe2+. I've got my oxidized form, which is Fe3+. This time, we can see that they are both aqueous. They're both in the same phase, so I'm going to put a comma to separate them. We know then how to represent half cells. We also know how electrode potentials are measured. Now, we need to be able to look at combinations of elements, be able to work out what reaction is going to take place, and also what the EMF or the voltage of that cell is going to be. Now, to write an equation, we can use the anti-clockwise rule. Okay. Now, to do this, the example I've got here is the iron and lead cell. The first thing you're going to do is order your equations from most negative to most positive. I have already done that here. Okay, so I've got my most negative on top, my least negative on the bottom, and I'm then going to use the anti-clockwise rule. So what this tells me is that my iron reaction is going to go backwards and my lead reaction is going to go forwards. Now I'm going to combine these equations. So I've got Fe solid, and then I've written the beginning of this one. So now I'm going to write the beginning of my lead equation. Plus 2 electron. Make sure I include my state symbols. And then I'm going to finish off my equation. Finally, I know I've got 2 electrons on either side, so I'm going to cancel those electrons. So that is my equation. Now, just to make this clear, iron is more negative. Iron has acted as a reducing agent. Lead is more positive or less negative, so it has acted as an oxidizing agent. It has become reduced in the process. The next thing I want to be able to do is calculate the EMF. Well, to do this, I'm going to take the electrode potential of reduction and take it away from the electrode potential of oxidation. In this case, my electrode potential of the thing being reduced was lead, Pb, which was 0.13, or minus 0.13, and then I'm going to subtract my electrode potential of iron, which is going to give me minus 0.13 minus 0.44. This is going to give me an EMF then of positive 0.31. And a huge thing is if my EMF is positive, that means a reaction will occur. If my EMF is negative, that reaction will not occur. So that's a nice way of checking when you've done your equation and you've looked at your oxidation and your reduction. Always think, right, is it negative? Should it happen? Here are some questions for you to try. So you can pause the video now. Here are some more questions for you to try. Just note that this table is giving you all of the information for questions 5 and 6. Here are your answers to questions 1, 2, 3 and 4 to check. And here are your answers for questions 5 and 6 for you to check. Hope this has gone well for you. Any questions, just come and ask your teacher. And hope to see you on another OMG video soon.